All right, well, that's good. All right, I think I got it going now. Okay, cross your fingers, that works. And I will be able to post that today. Okay, so when we are looking at substances, sometimes they will have you try to figure out different ratios. I don't know why this all highlighted, but it did. So when they are combined to form a mixture, we have these mixtures, the amounts can vary. And you're actually going to get a mixture, I think it's in unit 4, and you have to figure this stuff out from experimental trials. So you have to do a titration with it and then figure out the percent iron in that mixture. And everybody's samples are different. Okay. So mass percent, then you can take the mass of the substance and divide by the total mass of the mixture times 100. That's going to give you your mass percentage. Okay. And what we're going to do is, this is commonly done as a combustion analysis. So they'll take some sort of substance and they will burn it. The carbon then in that sample is all converted into carbon dioxide, and all of the water is converted into, or I'm sorry, all of the hydrogen is converted into water. Okay, so if you remember your combustion reaction from back in regular chem, you had, and I guess I should do this up here so people can see it. I've got the recording. You had some sort of hydrocarbon. You had oxygen from the air, and from that you produced carbon dioxide and water. Okay. So all of the carbon from this guy is going to go into here. All of the hydrogen is going to go into your water. So if you can measure these and figure out what amounts they're in, then you can backtrack and figure out how much carbon you had here and how much hydrogen you had here. Okay. And that's called combustion analysis. We can do this optically. We can do like light. Oh, shoot, I forgot. That's not gonna, doesn't travel. Okay. So you can do it optically using the Beer-Lambert law, which we will get into in unit 3, where we use the spectrophotometers. You can do it by mass, which is typically what these problems end up having you do. And then there's also this photoelectron spectroscopy, which we'll get into a little bit tomorrow. No, not tomorrow. Tomorrow's, well, we start getting into periodic trends. So, all right. I do get into the math of this whole thing. All right. So we have our calcium carbonate. And that calcium carbonate, no, that's what we do. I'm reading the wrong one. Okay, aluminum. Sorry, my bad. Aluminum and oxygen are coming together. Okay, and they're forming aluminum oxide. And we have a sample mixture of aluminum oxide. They've given us the mass of that. And they've given us the mass of the aluminum. So they want us to balance the equation. So I've got even and odd. I'm going to double the odd. Remember that? Yep. Okay. So I've got 2 here. I've got a 3 here. So I'm going to put a 2 here for my coefficient. That's going to give me 4 aluminum. And it's going to give me 6 oxygens. So I've got my equation balanced. So number 1 is done. What is the mass of the oxygen that was in the sample? Well, if we know how much the sample was, and we know how much the aluminum was, all we have to do is subtract, and it's going to give us the mass of the oxygen. Okay. So if I subtract those two values, I should end up with 0.59 grams. So here's my B. I'm going to take the mass of the sample minus the mass of the aluminum. And that's going to give me 0.59 grams of O2. What is the mass of the aluminum oxide? What mass of aluminum oxide was in the mixture? Okay. So if I know my oxygen amount, I can use my wonderful, and I know you guys love this so much, dimensional analysis to help you. Yes, yes, yes. Thank you. Thank you very much. So I'm going to take my, I know have my known amount of oxygen here. I'm going to convert that into moles. Did I lose anybody with this value? Got it from the periodic table. It's 2 oxygens, 16 plus 16. Okay. Then I'm going to do a mole ratio. So I'm going to take my moles of O2 and my moles of Al2O3. And I'm going to get those values from my balanced equation. So for every 3 moles of oxygen, I end up with 2 moles of this guy. And then I'm simply going to take that and take my moles into grams. So I'm going to take 2 aluminums, 27 each, and 3 oxygens, which is 48. I'm going to add all that together. I'm going to get 101.9.
Attention staff, you may have noticed the campus is a bit slow this morning. So if you need to take attendance manually, please do so and run your sheet. Have a student run your sheet to the attendance office. Thank you.
What, honey?
Where did you get the 100?
I added 2 aluminums at 27 each and 3 oxygens, which is 48. Yep. So 54 and 48. All right. So I got that value. I get 1.3 grams of Al2O3. Good. Good. Okay. All right. So then, what is the mass percent of aluminum oxide in the aluminum and aluminum oxide mixture? Well, we know that 1.3 grams is the mass of the aluminum oxide. We got that from right here. Yep.
You said that like two of the aluminum is like 54, for the oxygen is 48. Would that be 102 instead of 101?
Yeah, I just found it. I'm just grabbing those values off of my head because I didn't look at a periodic table, but good. All right, so I've got this guy. So for D here, which I've run out of space for, anybody still need this up here?
No.
Okay. So I'm gonna get rid of this and give me some space. So I'm gonna take that 1.3 that I calculated in C, and I'm gonna divide it by the mass of the mixture, which is right here. So 120.91 times 100, that's going to give me my mass percent. And that ends up being 1.1%. I'm going to skip the we do. If you go home and use a QR code scanner, like your camera on your phone, you can watch a video of that one. I'm moving on to 1.5 because I want to make sure we got enough time to cover everything. Okay. Good. Okay. All right, 1.5. 1.5 is, oh, we are going to be talking about Coulomb's law a little more starting tomorrow. You will never have to solve anything with Coulomb's law. And we talked about Coulomb's law last year when we talked about periodic trends, if you were in honors. We may have talked about it a little bit in regular. I don't remember. I know I covered it in honors quite in detail. So Adam's done. We've got our different values here. You've got your principal. This is your quantum numbers. Okay. So from your quantum numbers, we did a colored periodic table back in the day with the different columns, like your S block, your D block, your P block, your F block. So that's what the quantum numbers are. Okay. There are no quantum numbers on the AP exam. Okay. But if you understand where those quantum numbers come from, and that's how I teach electron configuration, then it's easy to do electron configuration. This is your 1s2, 2s2, 2p6. Remember that whole string? Okay. So that's what this is talking about, just kind of dusting off those cobwebs. We have the different orbitals. This is your s orbital, your p orbital. When we get into hybridization in next unit, we'll talk a little bit more about those orbitals and their shapes and how they hybridize. Just talking about the different orientation in space and then the different energy levels. Okay, we talked about how much each energy level can hold. We have these different shells. Remember, your S block can only hold 2 electrons. Your P's hold 6. Your D's hold 10, and your F's hold 14. Okay. So we'll talk about more about shielding and everything coming up in periodic trends later this week. And these are your rules for your electron configurations. So remember, you have to fill the smallest subshells first. Then you have to have 1 electron in each shell or in each orbital before you can double up. And then you have to have them opposite spin when they're in that orbital. And this is the AFA diagram. This is what I had to memorize in when I was going through chemistry because nobody taught me quantum numbers. But you can use your periodic table and then you don't have to memorize this thing if you just follow it numerically. And when I taught you this, I taught you about chutes and ladders. Remember, you started and you keep going through until, yeah. Okay, so you've got your principal energy level, you've got your subshell type, and then how many electrons are in there. If you add up these values, these superscripts here, that'll give you your atomic number for the element. So this is lithium. I don't even need to look at any of the other stuff. I can add 2 and 1 together, go to the periodic table, find number 3, it's lithium. Okay. We also have the shortcut where you can go to the previous noble gas. If this is the noble gas, if this is what you're identifying as argon, you got to go all the way back to neon then. Right? So you have to go back to the previous noble gas and you put that in brackets and then you start off from there. It's like taking your ladder up. All right, arsenic. Arsenic. Find arsenic on your lovely periodic table. Arsenic is number 33, yes? Is that correct?
Yes.
Okay. All right, so I'm going all the way to here. So I'm going to start, remember my helium, when we're doing quantum numbers, we throw helium over here. Okay. So helium, hydrogen helium is 1s2. Okay. Then I'm going to go 3 and 4. So that is my 2s2. Then I'm going over here. That's going to be my 2p6. Numerically, I go from 10 to 11 down here. So that is my 3s2. Then from 12, I'm going over to 13 and I'm grabbing all of these guys. So that's going to be 3p6. Then I go down here. That's going to be my 4s2. Now, this is where it gets a little tricky. Get out your dust rag. When you go over here, it's not 4 anymore. It's 3. It's period minus 1. So this is 3D 10. That takes me over to gallium. And then I need to pick up these last 3 here. So that's going to be 4p3. Okay. If I want, unless they specify that you have to do this the long way, you can always use noble gas configuration. Okay. So if I wanted to do noble gas configuration, I'm going to go back to my previous noble gas and I'm going to take all of this stuff and I'm going to represent it in brackets. So I would do a bracket. My previous noble gas would have been argon. So I would go AR, and then I would go 4s2, 3d10, 4p3. Remember that?
Yeah.
All right. This is an ion. When you go home and try to do this one on your own, this is an ion. So you're going to take 2 electrons away. Those 2 electrons are always going to come out of the nearest s or p orbital. Okay. So for calcium, you're going to actually end up pulling those 2 electrons away. Okay. And you'll actually stop with your electron configuration. Actually, I can do that one for you. There's the electron configuration for calcium plus 2. So I took 2 electrons away. Because it would have been 4s2 here. This became positive, which means we've taken 2 electrons away. Gone. So there it is. And if you want a more detailed explanation, scan the QR code. All right. Last but not least, photospectroscopy. You ready? I gotta erase all of this. My shoulder's getting a workout today, y'all. Okay, so photoelectron spectroscopy. When we are looking at this, what they do is they go through and they shine in some radiation, typically UV or X-rays in, and they can begin to pull electrons away. Okay, and they're going to pull them away from the furthest thing out first. And as you pull those electrons away, it's going to take less energy to pull them away when they're further out. When I taught you periodic trends, I talked about a mom, okay? And I talked about how when that mom has a baby, it's newborn, right? She holds it really close, okay? It's not getting away. And then good grief, just stop, thank you. As we move and become a toddler, still hold on to the hand. It's going to be hard to pull them away. And then when they go off to elementary school, it's a little easier to pull that kid away until we get all the way to the 7th electron shell and they're off at California living their life, right? Mom's back here in Wisco. Okay, little easier. So as they move further away from the nucleus, or mom, as they move further away, it's easier to pull the electrons off. And that's what they're doing here. They're pulling them off. This is how much energy it takes. So the first thing you need to do when you get one of these diagrams is you need to look at the x-axis, because some of these are drawn with the nucleus being over here, and some of them are drawn with the nucleus being on the opposite side. The way you know that the nucleus is here is it's a bigger number, because it's going to take more energy to pull that kid away. That newborn baby, mama's, you don't get this baby. Okay. Good. All right. Then you look at number of electrons. Okay. So I always find my nucleus. So my nucleus for this guy is over here. And so this is going to be my 1s, and I've got 2 electrons there. Notice that there's a gap here. We've got distance. It's getting further away from the nucleus, so it's a little easier to pull away. So this is going to be 2s2. This then will be 2p, and I've got 6. And you could count the number of electrons. That's on your y-axis. And then finally down here, this is 3s1. Go and find that electron configuration or count your electrons. 2, 4, 6. That's 10. 11. Number 11 is sodium. Y'all are packing up on me like an advisory day or something. All right. So I think you can probably do, so go home, try to do all of the rest of this assignment. You've got a scan code here for this guy. You have a quiz tomorrow between 1-1 and 1-6. There will be one problem on there from 1-7, which is periodic trends. It is extra credit to. Good. But if you want to glance over periodic trends tonight, you might have a better chance of getting it correct. So, you know, I'm just telling you, it's there.